Bismillahirrahmanirrahim. Welcome to the lecture on CPU scheduling. In this lecture, we are going to discuss about the scheduling algorithms like first come first serve, FCFS, priority scheduling, round robin, and multi-level queue scheduling algorithm. Before we go into the lecture, let us discuss the basic concepts which are involved in this CPU scheduling algorithm concept. CPU burst time and input output burst time. So, CPU burst time basically refers to the amount of time a process needs a CPU. How much time a process needs a CPU. And input output burst time means it refers to the amount of time a process needs for performing input or output operation. So, in this lecture we will discuss about the short term scheduler. Just recall the concepts what we have seen in the lecture 2, the queuing diagram, and also the types of scheduler. There are two types of scheduler, one is short term and another one is long term. So, the short term scheduler chooses how to allocate the CPU between processes which are ready to execute. So, here this is the ready queue. Here set of processes are waiting for the CPU execution. So, just assume here many processes are waiting here. Now, we need a program which would schedule or arrange these processes in a specific order and allocate the CPU to these processes in that order. That program is called short term CPU scheduler. So, we are going to study about that short term CPU scheduler in this lecture. The short term scheduler can be classified into preemptive and non-preemptive. Okay. So, non-preemptive CPU scheduling algorithms would hold the CPU for their full burst time until they get terminated or they go to waiting queue to perform the input output operation. Okay, let me give some example. The example for the non-preemptive scheduling algorithm is first come first served scheduling. We will discuss shortly, but now I want to explain the concept of non-preemptiveness. So, let us assume there are three processes P1, P2 and P3. Okay, they are waiting in the ready queue. Okay, the ready queue which we have discussed just now, this ready queue P1 and P2, they are waiting for the CPU. So, now which process would get the CPU first, which process would get the CPU second, that would be decided by the scheduling algorithm. Example FCFS, and this FCFS belongs to the non-preemptive category. So what is this non-preemptiveness? The process 1 burst time is 24 milliseconds. That means it needs a CPU for 24 milliseconds. Process 2 burst time, CPU burst time is 3 millisecond. Process 3 has a burst time of 3 milliseconds. So the process 1 arrival time is 0, 1, and P2 arrival time is 1 and P3 arrival time is 2. So the process 1 came to the system first, so it would get the CPU first. So process 1 is getting the CPU, that is explained using a chart, and this chart is called Gantt chart. Okay. So the process 1 is getting the CPU. You can see the process 1 is holding the CPU to its full burst time. So it needs a CPU for 24 milliseconds. So it is holding the CPU for 24 milliseconds, and the CPU is not given to any other process until the P1 completes its task, until the P1 terminates. So if the scheduling algorithm allocates the CPU in this manner, that is, it gives the CPU to a specific process until the process terminates or the process goes to the input output queue. Okay, till then if the process is allowed to execute with the CPU, then we can call that type of algorithms as non-preemptive. So the P1 can hold the CPU until it finishes the until it terminates. It can hold the CPU for its full burst time. Similarly, P2 also can hold the CPU for its full burst time. P3 is also holding the CPU for its full burst time. Such kind of algorithms are called as non-preemptive. Now we will discuss one more another algorithm. Let us say the process same set of processes under the RR round robin algorithm. We will see how they behave, how this algorithm behaves. You can see the process 1 burst time is 24, but the process 1 is not holding the CPU continuously. Okay, it is holding for some time. We will discuss this little later. Okay, but just now the main objective of our discussion is what is preemptiveness and non-preemptiveness. So earlier the FCFS with FCFS I have explained the non-preemptive nature of scheduling algorithms. Okay, here I am explaining the preemptive nature of some scheduling algorithms. So the process 1 needs the CPU for 24 milliseconds, but it is not holding continuously. It is holding for 4 milliseconds, then CPU is given to P2, then P3, then again it is getting the CPU again after some time. Okay, so this kind of so when the process 1 is running with the CPU, after 4 milliseconds, at 4 millisecond, the process 1 is removed from the CPU and the CPU is allocated to the process 2. This is called preemptiveness. Removing the process from the CPU and allocating the CPU to another process. Okay, this is called preemptive property. So the scheduling algorithms can be classified into preemptive and non-preemptive. Okay, so that is what explained here. In this lecture we are going to discuss about these algorithms: FCFS, first come, then priority, then round robin, in short we can say RR. Then priority scheduling. The FCFS is actually non-preemptive in nature. It is non-preemptive. And the round robin is preemptive type of scheduling algorithm. The priority can be implemented either as non-preemptive or as preemptive. So let us recall the CPU scheduling algorithms can be classified into preemptive and non-preemptive. Okay, now you know already what is preemptive type of algorithm, how they behave, and also how the non-preemptive type of algorithms behave. So FCFS is of type non-preemptive. Priority scheduling is it can be of type preemptive or non-preemptive. Round robin is strictly preemptive. Okay, so multi-level scheduling means it's like implementing scheduling algorithm, set of scheduling algorithms together. It has combination of many algorithms, they work together, which we would discuss at the end of this lecture. So what is a dispatcher? So dispatcher is a program or module which exists in the kernel of the operating system. Okay, dispatcher program, it exists in the kernel, you know already, which we have discussed in chapter 2. The kernel is a very important part of the operating system. So inside the kernel you have a program that's called dispatcher. So dispatcher module gives control of the CPU to the process selected by the short-term scheduler. So short-term scheduler basically decides let's say P1, P2, P3, they are waiting here. So it decides, it arranges the short-term scheduler like round robin or FCFS or priority scheduling algorithms. They decide the order in which the CPU has to be allocated to the waiting processes in the ready queue. So the scheduler basically talks, schedules the specific order, but the program which allocate the CPU to these processes is called dispatcher. So dispatcher is the program which gives the control of the CPU to the process selected by the short-term scheduler. So short-term scheduler, they select the processes, they put the processes in an order, specific order, and the dispatcher give the control of the CPU to the processes selected by these programs, short-term scheduler programs. And also other functionalities of the dispatcher are as follows: switching context, switching from user mode to the kernel mode and from kernel mode to the user mode, jumping to the proper location in the user program to restart the program. So this is called context switching. When a set of processes are running in a system, okay, they share the CPU actually. So the CPU time is shared among a set of processes running in a system. So that is depicted using the concept of context switching. Let us say there are two processes running, process P0 and process P1. Process P0 initially executing. While the P0 is executing, the process 1 is idle because two processes cannot run with the CPU at the same time in a CPU at the same time. So process 0 is running. While the process 0 is running, process 1 is idle. Okay, it exists in the ready queue. It exists in the ready queue. So it is idle, it's ready. Okay. So now once the process 0 execution is temporarily halted, okay, by some interrupt or by system call, you can ask one question: why this process 0 is not continuously running? One example we will be discussing shortly is this one. There are many scenarios. One of the scenario is easy for you to understand at this moment. You can see the process P1, 24 milliseconds is the burst time, that is amount of time it needs a CPU. Initially it gets 4 millisecond. Okay, because the time quantum means each process can hold the CPU only for 4 milliseconds for each chance they are getting. So when the P1 gets a first chance, it can hold the CPU for 4 milliseconds. Then after the other processors they get the CPU, the P1 get the chance again. Okay, so after the 4 millisecond, after the time quantum period, what is happening here is context switching. That is, the process 1 is taken out from the CPU, and CPU is allocated to process 2. So when the P1 is taken out of the CPU, it is currently running, right? The process 1 is running. So when the process is running, for example, let's say some Java program, there are some calculations going on. So while the calculations are going on, please understand, some values would be in the memory, right? Let's say sum of two numbers. So while the program is doing some computations, some values would be in the memory. But just understand, the program has not yet completed its task. So while it has not yet completed its task, it is asked to give up the CPU. So what happens? The operating system would save the current state, whatever values in the memory, whatever values in the register, all these things would be saved. Its current state of the process 1 is saved. Why it has to be saved? Because it is going to move out of the process, move out of the CPU, and it will why it's running now. So after 4 milliseconds it would just go and wait in the ready queue for the next chance. You get the point? So when the running process is removed from the CPU, when the context switching takes place, the process current state, okay, whatever its values in the memory or in the register would be saved, and then the process would be asked to go to the ready queue. Okay. So that's what happening here. The process P0 running, context switching takes place. When the context switching takes place, it can be due to interrupt or system call. Okay. So when process context switching takes place, the currently running process state has to be saved into its process control block. I think chapter 2 or 3 you would have studied about the process control block. It is a structure which stores all the information about a process. Okay, so please recall here. PCB stores all the information about a process. What type of information? These are the types of informations like code section, data section, process stack, program counter, CPU register values, memory management information, memory values, accounting information, all these informations would be saved in its PCB. Each and every process has a PCB. If there are 100 processes running in a system, then there would be 100 PCB. For each process, there would be a unique PCB structure. Now, the process P0 is sent to the ready queue. So, its value, let us assume it has been sent to the ready queue. So, its current value is saved into its process control block. Now, let us assume the scheduler has selected the P1 as the next process which would be running with the CPU. So, process 1 is going to, it's currently waiting in the ready queue, it is going to run. So, before it, it starts running, its current state, its memory values, register values, all would be loaded into the memory and registers, okay, from the process control block. So, from its process control block, the system would read all the values and would load the values, whatever values applicable, into the memory, into the register, so that it would continue its operation. So, now the process 1 is running. While the process 1 is running, the other process, it's not running, it's a ready state, it's waiting now, okay, it's waiting for the CPU. And now let us say context switching is taking place, context switching. So, when the context switching takes place, now what happens, the process P1 state is saved into its process control block, and now let us assume the P0 is going to run again, because let us assume its burst time has not yet finished. So, its values from its process control block is loaded into the memory and registers, okay, its state is loaded, reloaded, and the P0 starts running. So, this is called context switching. This is how multiple processes in a system, they share the CPU. This shows, this context switching context, this concept shows how many processes in a system, how they share the CPU. For example, Control Alt Delete, if you press, you get the task manager, okay. So, you can see like many processes running concurrently in a system. There are many processes running, but we have like one CPU, maybe it has 1 or 2 cores or 3 cores or 4 cores, but how come all these processes, they can run at same time with a single processor? So, this is by this concept, context switching. They share the CPU in this manner, but it takes place so fast, so quick. We think that each program is running alone in a processor. They have a separate processor. We get that sort of feeling because the CPU is so fast and quick. So, this context switching is performed by the dispatcher. So, the dispatcher is the one which gives control of the CPU to the processors. It performs the context switching. It moves the system from user mode to the kernel mode. There are 2 modes, user mode, kernel mode. Okay, so it moves the system from user mode to kernel mode to user mode. Then another thing is moves the control to the proper location in the program. So, let us say when a program has 4 statement, okay, let us say A is equal to 10, B is equal to 20, then C is equal to A plus B, then print C. Now let's say a program, let's say P0 is running. This statement is finished, this statement is finished, but before the process completes this statement, context switching takes place. Context switching, context switching takes place. So what happens, these for this process P0, first two statements finished, statement 3 is yet to finish. So only when the statement 3 finishes, the program would terminate normally. Okay, but before that, what happened, the operating system has taken the CPU from the P0 process. So these values would be saved in its process control block, and the CPU is given to another process. So when this process P0 gets the chance again, okay, when it gets a chance again, the execution should start from statement 3, not from statement 1 again, correct? It should start from statement 3. So the dispatcher program would remember this. It would understand this current location of these where the instruction has to start again from the process control block, and it would do appropriately. So the dispatcher program would jump to the proper location in the user program and restart the program. Okay, otherwise what would happen, every time it would start from the beginning. Okay, so what is called dispatch latency, time it takes for the dispatcher to stop one process and start another running. So here you see the process 0 is running, now it is stopped, and the P1 is P1's execution starts. P0 stopped and P1 is made to run. So some amount of time would be wasted, correct? That is called dispatch latency. Time takes for the dispatcher to stop one process and start another process running. Now we are going to discuss some CPU scheduling algorithms like FCFS, priority, and round robin scheduling algorithm. There are many algorithms, and like shortest job first, etc. So we have so many algorithms. We have to compare these algorithms. We have to analyze them, and we have to understand their performance. So we need some criteria, okay, based on which we can compare these algorithms and come to a conclusion which algorithm is better, which algorithm. So we need criteria to analyze their performance. So these criteria are used like CPU utilization. It means keeping the CPU as busy as possible. So any algorithm should not waste the CPU time. The CPU time should not be wasted. The CPU should not be sitting idle. Okay, so you can see how much CPU time, percentage of the CPU is consumed here. Okay, so the CPU time should be efficiently utilized by any good algorithm. Throughput means number of processes that complete the execution per unit time. So basically it's like if there are many processes and the number of processes they are completing their task should be more, per unit time should be more. So turnaround time means like how much time a process spends in a system, amount of time to execute a particular process, how much time a process spends in a system. So it should be less. Okay, the turnaround time should be less, throughput should be more, CPU utilization should be more. Waiting time means like you just open waiting time means how much time a process is waiting for the CPU, how much time it is waiting in the ready queue. It should be less, actually the waiting time should be less. Okay, whenever it comes to the ready queue, it should get the CPU quickly. Response time means amount of time it takes from when a request was submitted until the first response is produced. So it's like when the process is getting the first response. So it's like, you know, you open a program but it's taking too much time to respond to you. So that means the response time is it's getting you taking more time to respond. So the response time should be less. Within short time that you should get your program execution should get the response. So the CPU utilization should be more, throughput should be more, turnaround time, I mean how much time a process spending in the system should be less, waiting time should be less, response time should be less. So these are the you know, criterias by which we can analyze the different algorithms. So preemption, in a non-preemptive scheduling system, a process keeps the CPU until it switches to the waiting state or it terminates. Already we have discussed this. Example, FCFS algorithm, a process will have the CPU, keep the CPU until it switches either to the waiting queue or it terminates. Till then the process can hold the CPU as far as the non-preemptive algorithm is concerned. So when you start solving the problems, that time you would understand very clearly. In a preemptive scheduling algorithm, the currently executing process can be removed from the CPU at any time. So when a process is running, any time the process can be removed from the CPU before it finishes its execution, before its burst time gets over. So these are the basic facts about the preemptive system. Just go through that. So what is a Gantt chart? Okay, so we are going to solve the algorithms. To understand the way algorithm functions, control flows, you know, we need a diagram which would depict the flow of control in a CPU scheduling algorithm. So it would show depict clearly the order in which the process going to get the CPU. So this is the Gantt chart. The chart what you see here is the Gantt chart. So this is the input data for the algorithm. Okay, so from that input data, you know, to understand the behavior of the algorithm, we have to draw the Gantt chart. From that we can understand the order in which the processes would be allocated the CPU. Okay. So let us solve some algorithms. First one is FCFS algorithm. The simplest method is to execute the process in the ready queue on a first come first served basis. When a process becomes ready, it is put at the tail of the queue. When the currently executing process terminates or waits for the IO, then the process at the front of the queue is selected. So let's say these are the three processes in the ready queue, P1 and P2 and P3. So which process arrived to the ready queue first? P1 arrived to the queue first. So it would be in the front of the queue. Which process came last? P3. So it would be at the end of the queue. Okay, so you know this queue. This queue. Okay, just assume the P1, P2, P3 they are here. So P1 the process would be put in the order as far as this algorithm is concerned based on their arrival time. So the process which arrives to the ready queue first, okay, would be scheduled first to the CPU. So here in this example, P1 arrival time is 0, so it came to the ready queue first, so it would get the CPU first, and it can hold the CPU until its burst time finishes. So P1 is first, okay, then okay, so P1 here 0, okay, 0, the process 1 execution starts at 0 and it holds the CPU to its burst time 24 milliseconds. Then after that, process 2 get the CPU, then it can use the CPU for 3 milliseconds, so 24 plus 3 is 27, and then process 3 get the CPU because its arrival time is 2, 27 plus 3 is 30. So this is the Gantt chart here. P1 getting so P1 is coming at 0 millisecond and immediately it is getting the CPU because this process came first, it's getting the CPU immediately. So just now we discussed that any algorithm we have to use some criteria to analyze their performance. Okay, so one of the criteria is waiting time, and another one is called turnaround time. So we shall use the both criteria here to analyze the waiting time and turnaround time. So the process 1 got the CPU at 0 millisecond minus its arrival time is 0, so its waiting time is 0. So how much time it was waiting in the ready queue? 0. It immediately gets a CPU. So process 2 actually gets the CPU at 24 millisecond and its arrival time is 1, so 24 minus 1 is 23, so its waiting time is 23 milliseconds. It's waiting 23 milliseconds in the queue. And process 3, it is getting the CPU at 27 milliseconds and its arrival time is 2 milliseconds. 27 minus 2 is 25. So total waiting time is 0 plus 23 plus 25 is 48. Average is 48 divided by 3. So the amount of time the processes average waiting time for these 3 processes in the ready queue is 48 divided by 3. So please understand, students, this is the Gantt chart. So when any problem is given, okay, first you should depict the Gantt chart that shows the order in which the processors would be getting the CPU and also the frequency, how many times they get the CPU would be shown through the Gantt chart. Here, however, each process get the CPU one time and they hold the CPU completely until their burst time finishes because it's non-preemptive. Okay, then from that you have to calculate the waiting time to analyze their performance. So this algorithm, so when you understand the way this algorithm functions, behaves, it's easy to construct the coding process. You can code this algorithm and do the implementation, and then you can analyze their performance using C or C++ or Java code. Now let us discuss another scenario, another problem. So there are 3 processes, P1, P2 and P3. So process 1 arrival time is 2, So process 2 arrival time is 0 and process 3 arrival time is 1. So this one comes first, this one comes second, and this one comes third. So naturally the order in which they get the CPU also is going to change. So process 2 gets the CPU first, it gets the CPU at 0 millisecond and it can hold the CPU until 3 millisecond. Then the process 3 gets at 3 millisecond and it can hold the CPU for its full burst time of 3 millisecond. And finally the P1, since its arrival time is 2, it comes late, it is getting the CPU at 6 millisecond and it can hold the CPU for 24 millisecond. This is the Gantt chart. Now let's calculate the waiting time. Process 1 waiting time is 6, it is getting the CPU at 6 milliseconds. 6 minus arrival time is 2, so 4 is the waiting time. Process 2 is getting the CPU at 0 millisecond, its arrival time is 0, so its waiting time is 0. Then process 3 is getting the CPU at 3 millisecond, its arrival time is 1, so its waiting time is 2. So 4 plus, total is 4 plus 0 plus 2 is 6 milliseconds. Average is 6 by 2, sorry 6 by 3, it's equal to 2 is the average. So what are the advantages and disadvantages? The algorithms are easy to understand, easy to implement. The disadvantage is waiting time not likely to be minimal. So when it is compared with other efficient algorithms, the waiting time is going to be more. Convoy effect, lots of small processes can get stuck behind one big one. So what's this mean? The process 1 here in this first example is getting the CPU first, right? The P2 and P3, they are very small, but they have to wait for long time to get the CPU. They are waiting long time behind a big process. So this is called convoy effect. Then poor response time. The response time means the time between the submission of the job and the first initial response what you get is very poor. So it's not good for the time sharing system, which we have discussed in the chapter 1. One more thing which I want to discuss here in this is turnaround time. Turnaround time. It's very easy to calculate. Let's say for this problem, the second scenario, let's say process 1. What time the process 1 is finishing its task? 30 millisecond. So process 1 turnaround time is 30 millisecond minus its arrival time. So what is its arrival time? Process 1 arrival time is 2. 2 is equal to 28. Then let's go to the process 2. Process 2, what time it is finishing? 3. arrival time is, process 2 arrival time is 0. So 3 minus 0 is 3, and process 3 arrival time is, sorry, turnaround time is, it is finishing its task at 6 millisecond, getting terminated at 6 millisecond. Its arrival time is 1. So 6 minus 1 is 5. So please understand, process 1 turnaround time is 28 millisecond. Its waiting time is 4 millisecond, but its turnaround time is 28. That means it spends 28 milliseconds inside the system. The process 2, this waiting time means how much time it is, it was waiting in the queue, ready queue. So how much time, total time it was spending in the system is turnaround time. So process 2 turnaround time is 3, its waiting time 0. Process 3 turnaround time is 5, its waiting time is 2. So similarly you can add and calculate the average turnaround time average. So turnaround time is very simple to calculate. Just go to the end, find process termination time minus the arrival time. So with this we conclude the FCFS algorithm, and let us move on to the other algorithms. Let us work out another FCFS algorithm problem. So process P1, P2, P3, there are 3 processes. Their arrival time is given here, and their individual burst time is given. So based on the arrival time, process P1 gets the CPU first. It runs for 5 milliseconds. Process P2 gets the CPU next. Then process 3 gets the CPU. So process 2 from once the P1 finishes at 5, P2 gets a CPU from 5 to 10 millisecond it runs. Then process 3 runs third, 10 plus 4, 14. Now let me show another way of calculating the waiting time. The same technique only, but this is more organized in a tabular form. It's easy to compute for you. First, let's calculate the turnaround time. The turnaround time is equal to completion time minus arrival time, AT arrival time, CT completion time. So for process P1, the completion time is 5, and process 2, the completion time is 10. You can see here. Process 3, the completion time is 14. And these are their burst time, and these are their arrival time. Now the turnaround time is equal to completion time minus arrival time. So completion time for P1 is 5, 5 minus arrival time 0, 5 minus 0 is equal to 5, that is the turnaround time for P1. And turnaround time for the P2 is, completion time of P2 is 10, you can see, minus arrival time 4, so 10 minus 4 is 6, that is its arrival time, turnaround time. Similarly for process 3, the completion time is 14 and arrival time is 10, so 14 minus 10 is 4. So individually we have calculated their turnaround time. Now let's go to the waiting time. Waiting time can be calculated using this formula. Waiting time of a process is equal to turnaround time of a process minus burst time of a process. So let us calculate the P1 waiting time. Turnaround time of P1 is 5. 5 minus its burst time. 5 minus 5 is 0. So that is its waiting time. And similarly, the P2 waiting time is turnaround time of P2 6 minus burst time of P2, that is 5. 6 minus 5 is 1. Then turnaround time of P3 is 4, and 4 minus burst time of P3 4. 4 minus 4 is 0. So now easily we have calculated the turnaround time and waiting time, and this is their total, and average is total divided by number of process, that is 3. Okay, here, so 15 minus 3 and 1 divided by 3 is the waiting time. Okay, so with this we conclude this FCFS part. Now let us move on to the round robin part, and then we will come back to the priority scheduling. Round robin scheduling is designed for time sharing systems, which we have seen in the chapter 1. The CPU time is sliced between different processes. Each processes would be thinking that they are running in a separate system. In the round robin scheduling algorithm, a time quantum factor is used, that is, how much time a process can use the CPU. Okay, so that is determined by time quantum. For each iteration, for each chance, how much time a process can use a CPU. The ready queue is treated as a circular list. So round robin scheduling algorithm, in the round robin scheduling algorithm, ready queue is treated as a circular list. So a process in the front of the queue would get the CPU first. So the process which comes first to the ready queue would get the CPU first. So the process would be allocated in the FIFO order, and they can run in the CPU for the period of time quantum. So once the time quantum is finished, and if the process has not yet completed its burst time, then it would come back to the ready queue. Okay, it would be added at the end of the queue. So that's why we call this ready queue in the round robin as circular list. The CPU scheduler goes around the ready queue, allocating the CPU to each process for a time interval up to one time quantum. Now let us discuss the round robin scheduling algorithm. This is the data given to us. There are 3 processes, P1, P2, P3, burst time 24, 3 and 3. The time quantum is 4. That means each process can, at a stretch, in a single chance, they can use a CPU for 4 milliseconds, not more than that. So you can see here the process 1 burst time is 24 milliseconds. So it uses 4 milliseconds. Then after the 4 millisecond, the context switching takes place. The CPU is allocated to the process 2. However, the process 2, even though it has time quantum of 4, but its burst time is just 3 milliseconds. So it is finishing at 7 millisecond. 4 plus 3, 7. Then P3 gets a chance, because the round robin would be behaving as FCFS. It would shift the control to the processes in FCFS order. The process 3 gets the chance third. Its burst time also just 3 milliseconds, even though the time quantum is 4. It cannot hold the CPU until its time quantum because its burst time is smaller than the time quantum. So 7 plus 3 is 10. Now once the P2 finished, P3 finished, only one process exists in the ready queue, that is P1, and the remaining time quantum of P1 is 20 because already 4 millisecond finished. So remaining time burst time, the remaining burst time is 20 milliseconds. So after P2 and P3 finishes, P1 would get the CPU. Okay, it would run from 10 to 30 milliseconds. So now let us go, we will work out some tutorial problems here. Okay, after we discuss slides, we shall move on to the tutorial problems. Process P1, so this is another example. There are 3 processes, their arrival time and burst time are given, and the time quantum in this example is just 3. Here you have to okay, just a minute. So the process 1 gets the CPU first. The time quantum is 3 millisecond. It holds even though its burst time is 8, it holds the CPU for 3 millisecond. The remaining burst time is 5. 8 minus this is 8 is its burst time. Because the time quantum is 3, it holds the CPU, it gets the CPU for 3 millisecond, okay, in the first chance. So when the context switching takes place, the remaining at this particular moment, the remaining burst time for the P1 is 5 millisecond. Then the process 2 gets the CPU. Its burst time, total burst time is 4. Because of time quantum, it gets the CPU for 3 millisecond. So 3 plus 3 is 6. Now context switching takes place and its remaining burst time is just 1 millisecond. Then again you can see 6. Okay, here there is actually a thing you have to understand. Be careful. The P3 is not coming here. After the P2, you can ask that the P3 should get the chance, right? However, you see the P1 initially getting the chance. After 3 millisecond, context switching takes place and the P1 exits the CPU and goes to the ready queue at 3 millisecond. So please understand, before the process 3 comes to the arrive in the ready queue, the P1 is joining the ready queue before the P3. That is why actually the P1 is getting the chance before the P3. Let me repeat once again. The arrival time of the P3 is 4, correct? The P1 is getting the chance first. It is running for 3 millisecond. Okay, after 3 millisecond, okay, context switching takes place. Why 3 millisecond? Because the time quantum is just 3. So after 3 milliseconds, the process 1 exits the CPU and goes back to the ready queue. Okay, goes back to the ready queue. So the process 1 is coming back to the ready queue again in 3 millisecond. At 3 millisecond, you can see the process 3 is not existing in the ready queue. It is coming at 4. So P1 is arriving in the ready queue before the P3. That is why in the Gantt chart you can see the P1 is getting the chance again before the P3. So P1, now you see again it is running for another 3 millisecond. So once 3 millisecond finishes, here 3 millisecond finishes, and here 3 millisecond finishes, totally 6 milliseconds finishes. So the remaining burst time is just 2. Remaining burst time is just 2. Now the P3 is getting the chance again, okay, because the P3 arrived before the P2. Okay, the P2 is coming back to the ready queue at 6 millisecond. The P3 has arrived to the ready queue at 4 millisecond. So P3 is getting the chance, and the P3 burst time is 4 milliseconds. So it runs from 9 plus 3, 12, and remaining time is burst time is 1 millisecond. Okay, now P2 is getting the chance. So P2 runs for 1 millisecond. Okay, then P2 exits, then P1 is running and P1 exits, P3 runs and P3 exits. So this is the order in which they things happen actually. Okay, so let us compute let us work out a tutorial problem now. Okay, so here there are 3 processes. P1, P2, P3, okay, and arrival time is given, burst time is given, the time quantum is 4. So please understand, for only round robin algorithm the time quantum will be used. So process 1 is getting the chance first because its arrival time is 0. Since it came first to the ready queue, it is getting the chance first. It can run for 4 millisecond. Why it can run for 4 millisecond? Because the time quantum is 4. Because the time quantum is 4, then the context switching is taking place. When the time context switching taking place at 4 millisecond, the process P1 burst time would be 4. Why? Because from 8 already 4 millisecond finished. So when 4 millisecond already finished, okay, the P1 burst time is balance burst time is 4. Now the P2 has arrived to the ready queue second. So P2 would get the chance next. So P2 would run from 4, okay, until 8, and its burst time is 4. So the P2 burst time would be 0, would become 0. So now the P2 terminates, exits. Okay, it has used the CPU until its burst time. Then when the process 2 finishes, the third process which comes to the queue is P3. Okay, ready queue. So P3 is getting the chance. Okay, so when the P3 get the chance, it would run from 8 to 10. Why? Because its burst time is just 2. So 8 plus 2, 10, and P3 burst time becomes 0 and it terminates. Okay, when a process burst time becomes 0, it terminates. Now when the P3 terminates, okay, at this particular moment of time, all these process P2 and P3, they have finished. They have finished, and only process which remains in the system is P1. So P1, how much burst time is remaining for the P1? 4 milliseconds. So P1 get the CPU, it would run from 10 to 14, okay, and P1 burst time also becomes 0 and it terminates. It's very easy to understand. Okay, so from the round robin algorithm, it is easy for you to understand that the process can hold the CPU for each chance they are getting until the time quantum period. So after the time quantum period, the context switching will take place and the process has to go back to the ready queue. Okay. Now the calculation of turnaround time and the waiting time, let's see. I already told you, okay, the same logic we have to use here. Turnaround time is equal to completion time minus arrival time. Waiting time is equal to turnaround time minus burst time. So these details already you know, this burst time and arrival time already you know from the given input. The completion time we are calculating from the Gantt chart. So the process 1 completion time is 14 and the process 2 completion time is 8. The process 3 completion time is 10, and already we know the arrival time from the given input. Okay. Then let us calculate the turnaround time. Turnaround time is completion time minus arrival time. So completion time for the process 1 is 14 and arrival time is 0. So 14 minus 0 is 14. And what is the waiting time formula? Turnaround time minus burst time. So what is the turnaround time for the P1? 14. 14 minus its arrival time 0. 14 minus 0, just a minute, I made some mistake here. Sorry, turnaround time, the waiting time is equal to turnaround time minus burst time. So 14 minus 8 burst time give waiting time of 6 for the process 1. Similarly, for the process 2, the completion time is this. Using the completion time and the arrival time, we have calculated the turnaround time. 8 minus 1 is 7. So using the turnaround time and the BT burst time, now we are calculating the waiting time. So 7 turnaround time and the 4 burst time, we are calculating the waiting time. So 7 minus 4, according to this expression, we get 3. So this is how we calculate for P3 and find the total. Okay, the average is just, you know, divide by 3 number of processes. So this is one more problem. You can see process P1, P2, P3, their arrival time is given and their burst time is given and the time quantum is given. Okay, this is very important for you because it is little complicated, this problem. Okay, why? Because you see the arrival time of P2, it is 4 millisecond, but the time quantum is 3. That means the P1 is finishing at 3 millisecond. However, at 3 millisecond the P2 or P3 has not yet arrived into the ready queue. You get the point? So P1 time quantum finishes at 3 millisecond, but at 3 millisecond P2 not available in the ready queue, not available in the ready queue, and also the P3. So what happens? P1 again will get the chance, because in the ready queue only P1 available at 3 millisecond and P2 is coming to the ready queue only at 4 millisecond. Okay, so this is another problem. Okay, little twisted. Okay, please just go through this. So P1 is getting the chance first. It runs for 3 millisecond and the remaining burst time is 2, because 5 minus 3 is 2. Okay, then at 3 millisecond again P1 getting the chance. Why? Because at 3 millisecond, please see, P2 or P3 not existing in the ready queue, they are not available in the ready queue. So P1 again get the chance and P1 again run for 2 millisecond. 3 plus 2 is 5 and P1 burst time becomes 0, it gets terminated. And at the 5 millisecond, of course P2 and P3 available. Why? Because 4 millisecond itself the P2 arrives to the ready queue and P3 arrives at 5 millisecond. Okay, so both P2 and P3 are available at this particular moment of time, this moment of time at 5 millisecond. P2 and P3 are available. Since P2 arrived to the ready queue before the P3 and after the P1, so P2 is getting the chance, okay, next to the P1. After the P1, P2 is getting the chance in FCFS order. Okay, first the process comes, whichever process comes first, they will get the chance first. So the P2 runs for its burst time 5 plus 3 8. P2 burst time becomes 0 and it terminates, and now the P3 is getting the chance. Okay, finally 8 plus 2 10, and P3 also terminates. And of course, students, you all know how to calculate the completion time from the Gantt chart. You have to find, then using the completion time, you know how to calculate the turnaround time, and you know how to calculate the waiting time using this formula. Okay, so this is what I want to talk about the round robin algorithm. And let us discuss some facts about the time quantum. The basic idea here in this slide is that the time quantum should not be small, as well as it should not be very big. Okay, it is should be a medium value. If the time quantum is very large, okay, you can see that the round robin algorithm would function like a FCFS algorithm. For example, in this case, students, now let's say you take a process, okay, the first process P1, just find what is its burst time, 5, right? So let's say now the burst time is I make the time quantum as 5. Now if I make the time quantum as 5, you can see this algorithm, round robin algorithm, would work like a FCFS. Okay, the algorithm which we discussed initially, the first algorithm, FCFS, it would work like a FCFS if the time quantum is very large. So the time quantum should not be big. Okay, if the time quantum is set to very small, we can talk of processor sharing. If we make the time quantum the same as the context switch time, we will spend half of our time on context switching. So that is the point here is when context switching takes place, understand some amount of time is wasted here. For context switching also some amount of time is wasted, which we are not considering in this calculations. You understand? Assume that some amount of time is wasted here in the time quantum. So if the time in the context switching, some amount of time is wasted. So if the time quantum is going to be very small, then there would be many context switching in taking place in a particular algorithm. So if too many context switching exist, then amount of time wasted in the context switching also increases. So the basic idea here is the time quantum should not be large. If they are very large, it would behave like a FCFS algorithm. Okay, and the time quantum should not be very small. If it becomes very small value, then some amount of time would be wasted on context switching. So this is what you have to understand. Clear? So are advantages. If the time quantum is big, we get the disadvantages of FCFS scheduling. If the time quantum is small, we get faster response time but slower throughput. However, the time quantum should not be very small value. We know why, because some amount of time would be wasted in the context switching. Okay, so with this in the round robin algorithm, if the time quantum decreases, then it would affect the turnaround time also. So you can see if the time quantum size is 1 and there are 3 processors excuse me, 3 processors with CPU burst time of 10, if they are running, then the turnaround time would be 29. If the quantum size is 10, then they finish the next CPU burst and the average turnaround time is 20. If the time quantum increases, it decreases the turnaround time. So it is an important factor which you should be knowing. It is the time quantum is inversely proportional to the turnaround time. So this is what I want to tell about the RR. We have discussed about the round robin. Now we shall move on to the priority scheduling. In priority scheduling, each and every process would be assigned a priority number. Each process is allocated a priority when it arrives. And also it can be explicitly adjusted. The value can be set externally. The CPU is allocated to the process which has the highest priority. If in the ready queue there are two processes waiting, then the process which has the highest priority would get the CPU first. So this is the basics of this type of scheduling, priority based scheduling. Priorities are represented by numbers. So each and every process, they have some number which represent their priority. If the value is less, then it shows the highest priority. The process which has same priority are executed in FCFS manner. So here I shall show one example. So here there are three processes and their arrival time and burst time given. Along with these details, you can see the priority number also given. So process 1 priority is 2, the process 2 priority is 1, process 3 priority is 0. So which process among these three has the highest priority? If the value is less, then the priority is more. So the process 3 has the lowest value. That means its priority is high. Process 3 has the highest priority. Second highest priority process is P2. The third, the lowest priority process is actually P. So understand, the value, if the value is less, it shows the highest priority. So the priority based scheduling algorithm can be either preemptive or non-preemptive. It can be implemented both as preemptive as well as non-preemptive. Let us explore how the non-preemptive scheduling algorithm functions. So you can see there are three processes, their arrival time is given. So process 0 arrives at time 0, so it is the one which comes first. So at time 0, please understand, in the queue, ready queue, there are no other processes, only P1 is existing. So this priority based scheduling algorithm understand that the scheduling will be, the process will be scheduled based on their priority number. Okay. However, at time 0, only P1 exists in the ready queue. So there is no possibility for this algorithm to compare this process with any other process, because this is the only process existing at time 0. So the scheduler selects the P1 first. Why? Because no other process available. So there is no way to compare the priorities of the processes. So P1 get the chance first, and let us say this is non-preemptive. Non-preemptive means they can hold the CPU until they terminate or they move to the waiting queue. So here we are not discussing about the waiting queue, any input output operation. So the process can hold the CPU for its full burst time. So P1 is holding the CPU for its full burst time, 8 millisecond. No preemption, here preemption is not taking place. You know, the P2, you can ask, process 3 has the highest priority, P3 has the highest higher priority than P2, and P2 has the higher priority than the P1. But understand that when the process 1 comes to the ready queue, okay, at time 0, no other process. So obviously the scheduler would pick up the P1 and schedule the P1 as the first process with the CPU execution. Okay, now once the execution starts while the P1 is running here, another two processes coming to the ready queue at time 1 and time 2, and even though their priority values are higher than the the P1, the system will not replace the P1 with P2 or P3 until the P1 finishes. Okay, because this is non-preemptive algorithm. So a process is allowed to finish its execution. Okay, so as far as the non-preemptive priority scheduling concerned, P1 is finishing at 8 millisecond. So now you can see at 8 millisecond P1 has finished its work. Let me just it has finished. Okay, so let me make it red. This P1 is finished. Now P2 and P3 are waiting in the ready queue, and now the scheduler, that is the priority scheduler, would compare their priorities. Okay, so P2 and P3, it would compare their priorities, which one has the highest priority, which one has the lowest priority. You know that if the value is less, then the priority is more. So P3 value is less, so it implies that the P3 has the highest priority. Okay, P3 has the highest priority and higher priority than the P2. So the scheduler would pick up the P3 as the next process that would be allocated the CPU. So P3 starts the execution, its burst time is 4. So it runs until its burst time completes. So 8 plus P3 gets the CPU. So P3 runs until its burst time completes. So 8 plus 2, 10. So P3 is finishing here. So now the P3 also finishes. So once the P3 finishes, P3 finishes, the remaining process is P2. So P2 gets the chance finally, and P2 runs and it finishes its task at 14 millisecond. And already we have discussed this comprehensively in the round robin as well as in the FCFS. You know how to calculate the turnaround time and waiting time, so you can make use of this expression to compute that values. Okay, so this is how the non-preemptive priority scheduling functions. Now let us discuss how the priority scheduling functions in a preemptive manner. So this is the input data given. Okay, so obviously when you see this, you understand the P3 has the highest priority, the second highest priority P2 has, and the P1 has the lowest priority. However, at time 0, only P1 exists in the ready queue. So the scheduler picks up the P1 and allocates, the dispatcher allocates a CPU to the P1. So P1 get the chance, but understand at time 1, at this particular moment, at time 1, a new process is coming, P2, to the ready queue. The scheduler, whenever a new process comes to the ready queue, as far as the preemptive priority scheduling is concerned, whenever a new process comes to the ready queue, immediately it would compare the priority of the process waiting in the ready queue with the process which is currently running, that is P1. The P2 priority is higher than the P1, right? You can see it. If the value is less, it represents higher priority. So P2 has a higher priority than the P1. So what happens? Context switching takes place because it is preemptive scheduling. P1 not yet finished. However, since the P1's priority is lesser than the P2, the P1 is preempted, taken out from the CPU. So when the P1 is taken out from the CPU, it has finished 1 millisecond so far and 7 millisecond remaining in its burst time. 7 milliseconds remaining. Okay, so P2 is given the CPU now by the scheduler. So P1, where it will go? It will go to the ready queue again. It would go to the ready queue and it would be waiting in the ready queue in the ready state. So P2 is getting the CPU and it starts running at 1 millisecond. When the time reaches 2 milliseconds, please understand, a new process is coming to the ready queue. So when the new process comes, immediately it's an interrupt. What happens? The scheduler would compare the P2 which is currently running with the CPU, okay, the P2 priority with the P3 priority, and also it would compare with the P1, and it finds that P3 priority is higher than the P2, currently running P2. However, the P3 priority is higher than the P2. So immediately context switching takes place. Process 2 is removed from the CPU and the P2 goes to the ready queue. So in the ready queue, P1 and P2 are waiting now. So P3 is getting the CPU now. P3 getting the CPU. P3 starts running. So P3 finishes its burst time, 2 plus 2, 4, and P3 terminates now. So once the P3 terminates, you understand that there are two processes waiting in the ready queue. They are P1 and P2. So the scheduler would compare their priority and find the P2 has the highest priority. So again the P2 is getting the chance before the P1. Why? Because P2's priority higher than the P1. Don't get confused. If the value is less, it implies the highest priority. Understand? So P2 gets the chance. Okay, while the P2 was preempted, what was its burst time, remaining burst time? 3. It was 4, but 1 already finished, so remaining was 3. So P2 is getting the chance. 4 plus 3, 7. P2 finishes. Then finally P1 7 burst time is pending. So P1 gets the chance finally. 7 plus 7, 14. So P1 also finishes. So this is a comparison between the preemptive priority scheduling and non-preemptive priority scheduling. You can see they are not preempted. The process not removed from the CPU. But however, in the preemptive, what happens? The P1 is removed from the CPU when the P2 comes with a higher priority, and P2 is removed from the CPU when the P3 comes with a higher priority. Okay, they go back to the ready queue. So again, you know how to do these calculations. Okay, already we have discussed this. So this is what I want to tell about the priority based scheduling. So if two processes, they have the same priority, how the scheduler would schedule them? Then the scheduler would check their arrival time, FCFS. If their priority is same, then their arrival time would be compared. Whoever has come first, they would get the CPU first. And the priority scheduling algorithm can be preemptive and non-preemptive. So there is a sample program given, and you can work out this. Okay, so basically here you can see there is no arrival time. So what it implies that their arrival time is same. If no arrival time is given, that means arrival time is same. So if arrival time is same, what you have to do is, okay, the problem is very simple. Then you have to directly check their priority. So you can see the P2 has the highest priority, P2 first, then P1 has the next highest priority, then the P4 has the next highest priority, then P3 has the lowest priority. It is scheduled last, and you know how to calculate the waiting time according to the tutorial what we have discussed. One of the issue with the priority scheduling is the problem of starvation. Starvation occurs when a process waits indefinitely to be allocated the CPU. Priority scheduling algorithms are susceptible to starvation. Okay, so what starvation here? Now you see there are three processes. Okay, P1 is running smoothly, but when P2 comes, P1 is removed from the CPU, correct? Why P1 is removed? Because P2 has the highest priority. Now only three processes are here. Okay, when P3 comes, P2 is removed from the CPU. Why? Because P3 has the highest priority. Now there are only three processes. Imagine in a system the processes are keep coming, and you know hundreds of processes are coming and continuously flowing into the ready queue. Just imagine that scenario. You know, processes are keeps on coming, keep coming to the ready queue continuously. There is a steady flow of processes into the ready queue. So when in this scenario, just imagine what will happen to a process with low priority. The process, for example, P1, let's say it has the lowest priority. Just imagine like this, and all new processes are coming, n number of processes are coming, P3, P4, P5, P6, P7, continuously new process keep coming to the ready queue, and all their priorities are all their priorities are high. That means they has the low number, they have highest priority, and P1 has the lowest priority. So for example, in a system 1 day or 2 day or 3 day, okay, for many days, just imagine the system is continuously running, and new processes are coming to the ready queue and their priorities are high. What would happen? And just imagine P1 has the lowest priority. So just imagine what would happen to the P1. P1 has to wait indefinitely for a very long time until all the processes with high priority, until they finish their task. The process with low priority, example in this situation P1, it has to wait indefinitely. So this issue is called starvation. This issue is called starvation. Okay, imagine a process P1 is waiting for the CPU, and a stream of high priority processes are arriving, and if this process arrives sufficiently fast, P1 will never get the chance to execute. It has to wait continuously. So what is the solution to the problem of starvation? The solution is called aging. So the system, to avoid the starvation problem, it would monitor how long a process is waiting. If they're according to the amount of time they are waiting, to avoid the starvation, the system would increase the priority slowly, so that eventually a process priority increases and finally it gets the CPU, and thereby it avoids the starvation. You understand how much time it was waiting? That amount of, according to that much amount of time, the priority is increased. So this solution we call it as aging. Okay, So in the Windows operating system, Control Alt Delete, I do this and we get task manager. Okay, so here we have process and okay, so for example we can select a particular process, this PowerPoint, and you can see the priority. Basically the system has assigned a normal level priority. If you want, you can decrease the priority or you can increase the priority. Okay, so the highest priority, okay, it's real time priority, then second one is high level, then above normal, normal, below normal. So what you understand is the priority scheduling algorithm is implemented in all the operating systems, and processes they have some level of priority, and this priority is fixed by the operating system, and we can explicitly change the priorities according to the convenience. Is it clear to you? We can increase or decrease the priority. So basically the nice command in Linux is used to set the priority value for a process. Example, every process running on your system has a nice value. By default the nice value is 0. The process priority range is from -20 to 19. So if the value is less, that means priority of getting the CPU is high. The chance of getting the CPU is high. So -20 compared with 19 means a process with -20 has the high priority. The lower the number is better. The process with the low number will get more CPU time. A regular user can set nice value from 0 to 19. So if user is not root, not administrator, then the user can set nice value for a process from 0 to 19. And if the user wants to give the very high priority, negative values, then the sudo command has to be attached. For example, now the user wants to start a process. Vim is a editor like Nano or gedit. Vim is one of the editor. So wants to start this process with a priority value of 15. So nice -15 Vim. Okay, so for example, to launch a Vim with a priority 15, this is the command. Okay, and similarly you want to assign a very high priority. That means if you want to give some negative values, -15, okay, if the value is less, that means it represents higher priority. So sudo nice. Why? Because if the value is negative, okay, only the root can has the privilege to do that. Okay, so you attach the sudo command, sudo nice -, 2 times, okay, 15 Vim. So it would be assigned a negative value. Now a process is running and a process ID is given. Let's say 14475 is the process ID. For that you want to change the nice value. You want to change, let's say for this process whose ID is 14475. Let's say it's currently running with the ID with a nice value of 15. Okay, now you want to change to 7. That is, you want to decrease the value. If you decrease the value, the priority increases. The chance of getting the CPU also increases. So okay, so if you want to decrease the value, it can be done only by the administrator or root. So you have to add the sudo command, sudo renice 7, okay, 14475 is the process ID. Okay, for this particular process, please change the nice value from whatever current value to 7. Okay, so you need the sudo root privilege, so sudo command is attached. So you can practice this in the Linux and try these things here. So you want to know the nice value of any process, and then you can use this command ps, okay, or you can use another command top. So you have here, you can see the nice value here, ni of processes. These are the processes, process id, and the nice value is given, okay. So top command can be used, ps command can be used to find the priority values of your process. And if you want to assign a priority value to a particular process, then you can use a nice command. And if you want to change the priority value for a running process, then you can use renice command, okay. So now let's discuss the multi-level queue. So we have discussed the scheduling algorithm, okay, in detail. So this queuing diagram is the fundamental thing which you should be knowing to understand the scheduling algorithm. Already we have discussed. So here you can see a ready queue, right? One single ready queue. But practically in any system there would be many ready queues. There would be many ready queues, okay, like ready queue 1, ready queue 2, ready queue 3, okay. So they will have different set of processes, because processes in the system is not of same type. Some processes are non-interactive in nature, so that processes we call it as batch processes. Some processes are interactive in nature, okay, they respond to the user request. Some processes belong to the system, okay. So there are different categories of processes available in the system. So they are not put in the same ready queue, okay. This ready queue, they are not put in the same ready queue, but different ready queues are used, one okay, one for each category of processes. Now one thing is from these different queues, okay, among these different queues, which process would get the CPU first, okay. So among these different queues, okay, the priority scheduling algorithm would be used. So for example, batch processes, okay, the processes in this queue will be having the low priority. The processes here in the system processes category queue would have the highest priority, and the interactive processes of user would be having a middle level priority. So this is called, multi-level queue scheduling. So the scheduling applied to different queues of different set of processes. Split the ready queue into number of different queues, each with its own scheduling algorithm. Implement a scheduling algorithm to decide which queue is allocated next. Preemptive priority scheduling is often used. So the system, the batch processes, for example, let's take, it would have FCFS, first come first schedule or serve, you understand. So these processes would be, okay, for example here let's say there are 3 processes, P1, P2, P3. So P1, P2, P3, among the 3, which will be scheduled first, which would be scheduled second, that would be decided by a scheduling algorithm which is specific to this queue. Let's say example FCFS. So this queue is controlled by FCFS. Now let's say we have here interactive processes. So these two queues, let's say they are scheduled using a round robin scheduling algorithm. Here round robin scheduling algorithm, here round robin scheduling algorithm. So this scheduling algorithm would schedule the processes in these queues. Now the question is, we have 3 queues, so which queue process would be scheduled first among the 3? Which queue would be getting the precedence first? That would be decided by another level of scheduling algorithm, that is called priority scheduling algorithm. So this priority scheduling algorithm would control these 3 queues, and each queue would be having individual scheduling algorithms. Is it clear? So this is what I want to discuss in this lecture. So in this lecture we have discussed the preemptive and non-preemptive algorithms. Round robin is preemptive actually, it cannot be non-preemptive. FCFS is non-preemptive and it cannot be preemptive. SJF we did discuss in this lecture. Priority based scheduling algorithm can be preemptive and non-preemptive. So information about any process is saved in process control block. Dash CPU scheduling algorithm is only non-preemptive, FCFS. Dash CPU scheduling algorithm is only preemptive, round robin. So these are some of questions to analyze how much you have understood these concepts. So which CPU scheduling algorithm will behave like FCFS algorithm when its time quantum is increased, round robin? Okay, already we have discussed this. Which CPU scheduling algorithm suffers from starvation? Priority can be this round robin, priority and okay. So priority algorithm are susceptible to starvation, whereas the round robin it's not suffering from starvation problem as well as FCFS, but priority is susceptible to the starvation problem. The solution to the starvation problem is aging. Okay, so we have discussed various exercises about the scheduling algorithms. With this I conclude this lecture. Okay, thank you very much.